All right, we're in section 6.5. This is the last section in chapter 6 for us. And this is also, I think, the shortest section. There's not a whole lot really to cover here, but it's important nonetheless. So what we're talking about with this section here is the average value of a function. So pretty far back in your math education, you learn about the concept of averages. And in this particular section, when I talk about the average, I'm specifically talking about the mean. If you've had statistics, you should have learned that there's a lot of different ways of thinking about what an average actually is. The more accurate term that we use in statistics is measure of central tendency. So the mean is usually what people are talking about when they refer to an average, just in common speech. But there's other averages. There's the median, there's the mode, and things like that. But yeah, that's kind of what we're talking about here. So when you first learn about averages and means, you're taught that if you have a finite set of numerical data, so I'm going to use y1 through yn as my numerical data, and it could represent all kinds of things. It could be the heights of a population of 10-year-olds in a particular town, or it can be the it can be all kinds of different things. For some reason, an example is not coming to mind. We take the average or the mean by adding up all of this data and then dividing by however much there was. So in this case, it would look like y1 plus y2 plus all the way through yn, and ignore that comma there, that's a typo, divided by n. Okay, so that's great. That works for finite sets of data, but there are actually applications where the average that we're looking for would concern an infinite set of data. An example could be average temperature in a particular region. So if I say, the average temperature in Sacramento over the course of the year is like 79 degrees Fahrenheit or something like that, where am I getting that number from? Well, temperature varies continuously with time, and there's an infinite number of temperatures that we achieve over the course of the year, because if you go from 79 degrees to even 80 degrees, even though that's a 1 degree shift, there's an infinite number of values between 79 and 80, 79.1, 79.01, 79.2, and so on and so forth. And we would have hit all of those temperatures in between 79 and 80 degrees. So how do you take an average that has an infinite number of values in your data set? And that's the question we're trying to answer here. So we're going to take a specific perspective on where the data is coming from that we're trying to find an average for. We're going to assume that our data that we're trying to average is coming from a continuous function, f. And we're going to specifically look at a particular closed interval in the domain of that function. And whatever the outputs of this function are over that interval, those are the values that we're going to consider our data that we want to average, okay? So clearly, if it's a continuous function over a closed interval, f will generally take on infinitely many values, unless f is a constant function. But outside of that one example, if it's continuous, it should take on an infinite number of different outputs in that closed interval. To compute that average, like we've been doing throughout all of chapter 6 with our applications of the integral, we first start with an approximation. And then that approximation will be made accurate at some stage in this derivation here. And that's going to lead us to an integral eventually. But right now, let's suppose that we were just going to approximate the average value of our function f over this interval ab. We can do that using the same sort of thing that we've been doing throughout the section. Take this interval ab, cut it up into a finite number of little subintervals, okay? And then from each of those subintervals, you choose a single sample point, x1 star, x2 star, all the way through xn star. Because I'm using a finite number of subintervals, and thus a finite number of sample points, then I can plug all of these in to my function f and get a finite number of outputs. okay? That finite number of outputs is going to be the thing that I want to take the average of. So that would look like this: f of x1 star plus f of x2 star plus all the way through f of xn star divided by n, because there would be n of those total, okay? Now, this n, I'm going to change the way that this looks to better suit the definite integral that I'm trying to get to, okay? So we have delta x equals b minus a over n. And if you don't remember where this comes from, delta x is what we're thinking of as the width of each of these subintervals. We're assuming that all of the subintervals have the same width, okay? B minus a would be the width of this interval. So b minus a is the total width from a to b, and we're dividing that into n equal parts, which gives us the length of each subinterval as delta x equals this, b minus a over n. So I could solve this, and if I were to do that, I would get n equals b minus a over delta x. That's a pretty straightforward algebra problem to solve for n there. That gives me a substitution that I could use for this n in the denominator. So that's going to become this. I have my sum of values up here over b minus a over delta x. This I can, because I'm dividing by a quotient, I can think of that as multiplying by the reciprocal of that, which can be alternatively written this way: 1 over b minus a times this sum of values here times delta x. I can then distribute that delta x in to get this, and then I can think of this sum here more compactly in summation notation. So this sum can be rewritten this way. And now this looks really familiar. That summation looks like a Riemann sum. It's got the stuff that you generally see in a Riemann sum: f of some sample point xi star times your delta x here, and you're summing from I equals 1 to n. Naturally, if you let n get larger and larger, then what's going to happen is your subintervals are going to get smaller and smaller, which means the sample points that you're using to approximate your average value are getting more tightly packed together. And because they're more closely spaced together, our average is going to become more and more of an accurate approximation to the actual average value of our function over that interval. Okay? So if we let n go to infinity, we would consider that to be an exact average, what we're looking for. And that would also turn that Riemann sum into a definite integral. So here is what we have as our formula, let's say, that we're going to use for the average value of a function. You integrate the function over whatever interval we're looking for the average on, and then we multiply by 1 over b minus a. You can also think of this as taking that integral and dividing by b minus a, or dividing by the width or the size of the interval you're integrating over. So this is the definite integral of f of x dx from a to b divided by the width of your interval. Now, I mention it that way because if you move on to Calculus 3, beyond this class, and you look at the several different types of integrals that you talk about there's double integrals, triple integrals, line integrals, surface integrals. There's a whole bunch that you talk about. For each one of those, there is a corresponding concept of average value, and they all have a similar pattern. It's an integral divided by the size of the thing you're integrating over. You don't need to worry about that quite yet, but if you go on to Calculus 3, it's a pattern that you might notice that's kind of helpful to know. Let's work through an example. I want to find the average value of this function, f of x equals x minus 2x cubed, on the interval 2, 4. So using this as my formula, 2, 4 is the interval a, b. So I'm setting up this quotient. 1 over b minus a would look like 1 over 4 minus 2 in my example. My integral goes from 2 to 4, and I'm integrating this exact function right here. So that becomes x minus 2x cubed dx, okay? 1 over 4 minus 2 is 1/2. And then when I integrate, I'm going to get 1/2 x squared for my first term, minus 2 divided by 4, which is also 1/2 x to the 4th. As for my second term, this goes from 2 to 4. I'm going to start evaluating this, but I notice that there's a 1/2 in each term here. I can go ahead and factor that out, multiply it to that 1/2 and get a 1/4 out of this. That's just going to make the arithmetic a tad simpler, because now I'm just looking at x squared minus x to the 4th. Now I've worked through a few definite integrals now as we've moved through chapter 6. I am going to trust that you can handle the arithmetic that follows from here, okay? I'm going to end up with negative 57, okay? Now, is it an issue that my average value came out to a negative number? No, it's not. And I'm not going to go into all of the detail why. I think it's worth it for you to kind of think about that for a minute. I would advise graphing this function and specifically focusing on where the function lives over this particular interval, okay? Is my function taking on positive values, or is it taking on negative values over this interval for the most part? That's going to be your clue as to why the average here is coming out negative. But let's go ahead and move on. All right, another example. A cup of coffee has an initial temperature of 95 degrees Celsius in a room that has a temperature of 20 degrees Celsius. According to Newton's law of cooling, the temperature T of the coffee after little t minutes, so I have a capital T for temperature, lowercase t for time, measured in minutes, can be modeled by this function. T of t is equal to 20 plus 75 e to the negative t over 50. Find the average temperature of the coffee during that first half hour. Now, I forgot to mention it here, but capital T is going to be measured in degrees Celsius. That would keep it consistent with the temperatures that we're seeing here. Another thing I'm going to mention is this is not the last time we're going to hear about Newton's law of cooling. In fact, when we get to chapter 9, we're going to talk about differential equations, and we'll talk about how we can derive Newton's law of cooling for, similar kind of scenarios as this one. But for now, we're just going to trust that this formula works and just work with it. So I'm noticing here that time is measured in minutes. I want to think about everything as all measures of time now in minutes for consistency. So when we talk about a half hour, I need to be thinking of that as 30 minutes, okay? So how do I work this through? My independent variable is t, it's time, and we're looking for the average temperature during the first half hour, which that would correspond to the interval 0 to 30. Remember, that's the interval for my t variable over which we're trying to find this average, 0 minutes to 30 minutes. So using my average value formula, I have 1 over b minus a, which in this case looks like 30 minus 0, times the integral from 0 to 30 of my function, t of t, which looks like this, 20 plus 75 e to the negative t over 50 dt. Okay, so integrating this now, this is going to look like 1/30th. I'm going to get 20t. Now you can do this, you can integrate this exponential function using a u substitution. You can set u equal to negative t over 50 if you want. I'm going to show you what it comes out to. It's going to look like negative 3,750 e to the negative t over 50. And then we're going to go from 0 to 30. You work through this integration. Okay, see if you're getting the same thing I am. And if you're not, ask about it in the discussion forums. That's what those are for, okay? So if you evaluate this now, I'm going to get 1/30th times 20 times 30 minus 3,750 e to the negative 30 over 50, plugging that in for t there, minus, remember parentheses, Plugging a 0 in, that's going to go to 0. Plugging a 0 in here. A common mistake I see with people doing integration with exponential functions is they move too quickly and they say, oh, I'm plugging zeros in for my t's, so everything becomes 0. And that's not the case with exponential functions. If I plug a 0 in for t, I get e to the power of 0, which is equal to 1, not 0. And negative 3,500 or 750 times 1 is just negative 3,750. Okay? All right, this is arithmetic. If you work through the arithmetic, you're going to end up with 145 minus 125e to the negative 3/5. Oftentimes we leave our answer in that form. However, for my purposes here, I'm actually going to see what this comes out to if I plugged it into a calculator. Use an approximation symbol. This is approximately equal to 76.4 degrees Celsius. Now, the reason why I want to work that out with a rounded value like this, 76.4, is for the purpose of a sanity check. And again, what a sanity check is it's a way of verifying that the answer to your problem made sense. Your solution should make sense in the context of the problem. Is this a reasonable answer to get? Well, remember, our coffee started at 95 degrees Celsius, but it's going to cool over time because it's sitting in a room that is at a colder temperature than the coffee itself. So I need to be getting an answer that's less than 95 degrees Celsius, which is what I got. It will not make sense for the cup of coffee to become cooler than 20 degrees Celsius at any point, because what's influencing the temperature of the coffee? It's the room. The coffee will approach the temperature of that room. There is nothing that would make it get colder than that. So my temperature can never be less than 20 degrees Celsius. I'm getting something that's between 20 degrees and 95 degrees. So this doesn't mean I did it correctly necessarily, but it doesn't mean that I made a very obvious mistake and can rule that out as not being a correct answer. Okay? So great. Let's leave that one. We're very close to being done here. Like I said, this is a very short section. The last thing we need to talk about in 6.5 is the topic of the mean value theorem for integrals. Now, you should remember from Calculus 1 talking about the mean value theorem, or the MVT. We usually shorten it up to that. And that's specifically the mean value theorem for derivatives. If you want, you can go back and review what that is. But this one is kind of the counterpart to that theorem for integrals. In fact, you can prove this theorem using the old mean value theorem. There is an exercise in your book that shows you how to do that, or has you do that. I didn't assign that problem, but it's something you could do if you wanted to. So here's what the mean value theorem for integrals says. I'll talk about this red box in a minute, but more intuitively, if you have a function f and it's continuous on some closed interval a, b, then f will attain its average value at some value c between a and b. And to be clear on what that means, let's consider this little graph right here, okay? I have a function y equals f of x, and you can see its graph is curved right here, right? Or the curve that represents that function on this interval a, b is right here. The average value of this function is represented by this red line. Whatever the y value is here is going to be the average value of this function right here. Okay? Now, that kind of makes sense. Not necessarily, I can't tell just by inspection that red line is exactly correct, but it feels like it should be roughly correct because the average value should not be as big as your largest values that your function takes on, nor should it be as small as the smallest values. The purpose of an average is to tell you what's right about at the middle of all of these values, and that's where I'm seeing the red line, okay? But notice that this red line also intersects this blue curve as well. So that means that there's some value c for which, if it gets plugged into my function, the point that it leads to on the curve has the same output, the same y value as this average value right here, okay? So in other words, whatever the average value of your function is over this interval, you're going to find a specific input that gives you that exact average. So formulating that in terms of, the integrals and whatnot, if f is continuous on this interval AB, then there exists a number c in your interval such that f of c, so that's when you plug c directly into your function, is equal to the average value of your function, which we have formulated this way. Alternatively, we oftentimes will take this equation or this equality and multiply both sides by b minus a so that I get this. F of c times b minus a is equal to this integral. And the reason we do that is because, for a couple of reasons, but for the one I want to talk about, it gives intuition as to why this is correct. So think about this, both sides of this equality right here. On the left-hand side, I have an integral of our function over AB. And we know from the very beginning of our introduction to definite integrals, this can be thought of as the area under that curve over the interval AB, right? So that definite integral represents this blue region here, its area. The right-hand side, I can think of that as an area as well, if you think of it this way. F of c is this value right here. F of c, because I plug a c in and I get f of c. So I can think of f of c as the height of this rectangle right here made by this red line and the area underneath it. What is b minus a? Well, b minus a would be the width of that rectangle because the rectangle sits on top of that interval AB, so b minus a is this length right here, or width if I want to think of it that way. So really what I'm looking at is the length times the width of this rectangle. In other words, what it's saying is I can find a value c, which when plugged into my function f of x, I know it gives me my average, but it also gives me this rectangle whose area is equal to the blue area. Now, intuitively, why does it make sense that such a c should exist? Well, if you think about this blue region, the region under this curve, as water that's been trapped between two panes of glass. I like to think of it that way. You imagine you have a two-pane window and there's water trapped between it, and the water has frozen into this kind of weird shape, right? This kind of curved shape. If it heats up and the water melts, so the ice melts, it's going to level out, and that average value is exactly where the water would level out. Now, because you've taken ice and melted it, the mass has not changed. It's the same amount of water, but it's just leveled out into a rectangle instead of this curved area. So the area is going to be the same, even though the regions looked different. Okay, hopefully that made sense. Let's do one final example to wrap things up. At what time t in the previous example is the temperature of the coffee exactly equal to its average temperature during the first half hour? So the fact that this can be answered at all is what the mean value theorem is doing for us. The mean value theorem is guaranteeing that there is a time t in that first half hour. We're talking about this coffee example up here. It's guaranteeing that there is some time within that first half hour where the temperature of our coffee will be exactly equal to 76.4 degrees Celsius. And we just need to find at what time that occurs. Okay, so 76.4, so let's do it this way. Our function that gives us the temperature at a specific time t is this. I want to plug in some specific value c for that t there. So that would look like this. 20 plus 75 e to the negative c over 50. And I'm saying for what value of this c here will this come out exactly equal to the average temperature that we computed up here? So 76.4. Okay, I'm going to do a little algebra. So subtract 20 from both sides. 75 e to the negative c over 50 equals 56.4. Divide by 75, e to the negative c over 50 equals 56.4 over 75. Take a natural logarithm of both sides to eliminate that e. In fact, let's do a few steps. I can see that I need to take a natural log which will leave me with negative c over 50. Then I would need to multiply both sides by negative 50 to isolate that c. So I'm going to get c equals negative 50 times the natural log of 56.4 over 75. And again, I could leave this in that form, but I would rather plug it into a calculator to make sure that the result that I'm getting is something that makes sense. So if I plug this into a calculator, the value I'm going to get is approximately 14.25. Remember, C represents a time measured in minutes. So my answer is 14.25 minutes. How do I do a sanity check on this? How do I make sure that this is a reasonable answer? Well, I know that the time has to occur somewhere in the interval AB. It has to occur somewhere within that first half hour. And notice the answer that I got is between 0 and 30 minutes. So I am attaining my average within that first hour. And that's the thing that I am ultimately checking. If I got something that's not that, if I got a negative number, for example, which wouldn't make sense in this problem, or if I got 50 minutes, I would know that I did something wrong because it's not falling within the interval that I'm supposed to be finding that value in. Okay, so that's going to be it for 6.5, and that also wraps up chapter 6.